Okay, so we'll now construct the Lebesgue measure. On R. So recall that we have a ring. So we started with P, which is set of all AB, A less than or equal to B, and AB equals empty set if A equals B. On this we define mu equal to mu of AB equal to B minus A. And then we took R equals ring of finite unions from P equals ring of finite disjoint unions from P. And then if E equals union I equals 1 to n, EI in P 1 less than equal to I less than equal to n, EI I equals 1 to n, mutually disjoint. Then we define mu of E equals definition, this is the obvious one, sigma I equals 1 to n mu of E. Okay, so and then mu is a measure on R. Okay, and since you can cover R itself by union n in Z, n plus 1, so any subset can be covered by this, and this has finite measure, therefore mu is sigma finite. So now we are ready to bring about the method of Karathiotry. So we have here R, and it's the measure is mu, and then we have the hereditary sigma ring R, which is and there we have the natural outer measure mu star. So mu star of E equals inf of sigma I equals 1 to infinity mu of EI, E contained in union I, EI in R. So this is the natural outer measure which we have, and then we would have the mu star measurable sets S, and there you have mu bar is a measure equal to mu star, and then we saw that it also contains S of R. Okay, and therefore you have mu bar, an extension here, and mu bar on S bar is complete. Okay, since again R is the union of this, and therefore this implies that R itself belongs to H of R, and this implies that because it can be anything which can be covered by countable unions is in a member of H of R, and therefore you have that H of R being hereditary is nothing but the power set of R. So H of R is nothing but the power set of R. Now S of R we call equal to B is called the Borel sigma algebra. And S bar we call as the Lebesgue sigma algebra. Okay, and so the members of S of R are called Borel sets, and members of S bar are called Lebesgue measurable sets. And mu bar on S bar is called the Lebesgue measure. Now you can do the same thing, same construction on Rn for all n greater than equal to 1, with P equal to, as I said, pi I equals 1 to n ai bi. And then you do the R, and then you do the measure, and mu of pi of I equals 1 to n ai bi is nothing but pi I equals 1 to n bi minus ai. So in other words, this is the Lebesgue measure in R is the extension of the notion of length, and in R2 it is the extension of area, R3 volume, and so on and so forth. Okay, so Lebesgue measure, because it comes from a sigma finite measure on a ring, so it's also sigma finite. In fact, this itself tells you this relation itself tells you that it is sigma finite. Okay, so we have that. Okay, so notation. So henceforth we will use the following convenient notation because we should be somewhat systematic. So Lebesgue measure on Rn will be denoted m sub n. So in particular, m1 will be the Lebesgue measure in R1. Okay, and then the Borel sets sigma algebra. This notation is B of n and Lebesgue sigma algebra will be called L of n. Okay, so this is the notation which we will henceforth follow in this course. Okay, so definition: any measure on Bn is called a Borel measure. So in particular, the Lebesgue measure is an example of the Borel measure. Okay, so now we have some better look at some properties of the Lebesgue measure. Every countable set in R is a Borel set of measure 0. So proof: let A belong to R, and then you have singleton A can be written as intersection n equals 1 to infinity a plus 1 by n. And since this countable intersection of elements in P which are also in R, and therefore this belongs to S of R, that is, it belongs to B1. Okay, so singletons are in B1 implies countable sets because it's a countable union of singleton are in B1. Okay, so now what is measure of singleton A? Now this is a decreasing sequence, they are all a finite measure, and therefore when you have a decreasing sequence of sets and the intersection, so is nothing, when everything is finite, this is nothing but limit n tending to infinity of mu of a plus 1 by n, which is equal to limit n tending to infinity of 1 by n, which is 0. So implies measure of every countable set is also 0, because a countable set is a countable disjoint union of singletons, and therefore that proves this proposition. Okay. Next proposition. The Borel sigma algebra is also the sigma algebra generated by the open sets of Rn usual topology. Let me just write R for the moment. We will talk about Rn in a moment. It's the same. Anyway, it doesn't matter. That means topology means is a collection of all open sets. Now there's a smallest sigma algebra which contains that, and that is precisely the Borel sigma algebra. So proof. So let us take AB in R. Then A less than B. Then you have AB can be written as AB minus singleton A. Now singleton A we just saw belongs to B1, AB belongs to B1, it's a sigma algebra, and therefore this also belongs to B1. Every open set, so every open set is the countable union of intervals, open intervals, implies every open set belongs to B1, implies S of open sets is also contained in B1. S of open sets means the smallest sigma algebra generated by the open sets, that is also contained in B1. Conversely, AB equals AB union singleton A, and singleton A is the intersection n equals 1 to infinity of A minus 1 by n, B minus 1 by n. So this belongs to S of open sets. So this implies P and then R and B1 are contained in S of open sets. So this implies that AB belongs to S of open sets. That means P and therefore R and therefore B1, they must all belong to this, and hence the result. So hence the result. We have both way inclusion, and therefore now we know the Borel sigma algebra is nothing but the thing. So in general, if you have a topological space and you define a measure on it, and a topological space, then the smallest sigma algebra containing the open sets is called the Borel sigma algebra, even in an abstract setting, if you have an abstract topological space. So now, easy exercise to adapt these proofs for any n. Okay, so all these results are true both in R as well as R. example, M1 of AB equals M1 of AB equals M1 of AB, each is equal to B minus A, because each is got by taking or adding or subtracting a point which is singleton, which has measure 0, and therefore this measure is B minus A, so both of these are also B minus A. Okay, now let us take AB minus cross 0 contained in R2. So AB cross R2 cross 0 can be written as intersection n equals 1 to infinity of AB cross 0 1 by n. And again, this is a decreasing sequence, therefore the intersection, all of them have finite measure. We know the measure of this set, and which is AB into 1 by n, and therefore this implies a M2 of AB cross 0. The Lebesgue measure in R2 is limit 1 by n times B minus A, n tending to infinity, and that's equal to 0. So now you consider R equals set of all x0, x in R2. Okay, so the R can be considered, the x-axis can be considered as a subset of R2. Okay, so then you have that R is nothing but the union n in Z, n plus 1 cross 0, and therefore this, and these are all disjoint, and therefore this implies that M2 of R is 0. But M1 of R again is the union of all such intervals, each of them has measured 1, they are all disjoint, and therefore this is equal to plus infinity. So the Lebesgue measure of R itself in one dimension is infinity, but if you consider it as a subspace of R2 or any higher dimensional space, it is 0. Okay, more generally, Lebesgue measure of any proper linear subspace in Rn is given by, let's say, W, Mn of W equal to 0. Okay, so if you have any proper subspace, it will always be of measure 0. Now here's another example where several little things which we will observe. Okay, so any non-empty open set contains a non-empty interval. Therefore, Lebesgue measure of any non-empty open set is strictly positive. Q rationals countable implies measure of Q equal to 0. So Q complement, so R minus Q equals irrationals has measure infinity, and both are dense sets. So denseness and measure don't have any connection, because you can have a dense set of measure 0, namely Q, and then okay, even though it more or less everywhere. Okay. 3. E contained in R is a measurable set. Measurable means Lebesgue measurable. That means it belongs to the Lebesgue sigma algebra such that M1 of E is 0. So it cannot contain any open set. So this implies every open set must intersect E complement. This implies E complement is dense. So you can have a dense set of measure 0, but if you have a set of measure 0, its complement is always dense. Okay. In particular, M1 of E equal to 0, E closed, that means its interior is empty. This implies that E is nowhere dense. And 4, you have K in R compact, implies K is closed and bounded, implies M1 of K is always finite. So every compact set has only finite measure. So we will continue the examples next time.